Raising a wheel over a curb. You're trying to raise a bicycle wheel of mass m and radius capital R up over a curb of height h. To do this, you apply a horizontal force F, as you can see in the figure. This is the bicycle wheel, and we have a force that's being applied in order to make it over the curb. What is the smallest magnitude of the force F that will succeed in raising the wheel onto the curb when the force is applied in part A at the center of the wheel and in part B at the top of the wheel, and in part C, in which case is less force required? Okay, so if I look at the forces acting on this wheel, there is the force F we're applying at the center in the first scenario, and there is the weight mg. If it's a uniform wheel, it is at the center of the wheel. The curb has a height h, and therefore the perpendicular distance between the force F and the pivot point is r minus h. And at the same time, since this is the radius capital R of the wheel, using this right triangle, the perpendicular distance between the pivot point and the center of gravity is r perpendicular, which is square root of r square minus r minus h parenthesis squared. Okay, so the first task is to calculate the torque with respect to the pivot point, and this is my coordinate system here. So if I look at the torque due to this force F, the perpendicular distance is r minus h. R cross F using the right hand rule shows me that the sense of rotation is clockwise. It's a negative torque, so this is going to be minus F capital R minus h, the perpendicular distance. However, the torque due to the weight is r cross F, r perpendicular times F, gives me, using the right hand rule, 4 fingers point from the pivot to the point of application of the force and curl the fingers towards the force. The thumb points upward in plus z direction. So this is a positive torque. The sense of rotation is counterclockwise. So this is plus mg r perpendicular, where r perpendicular squared plus capital R minus h parentheses square is r square, using this right triangle here. So solving for r perpendicular, we have r perpendicular square plus r square capital R square plus h square minus 2 capital R h equals to r square. So these r squares will cancel. We find that the perpendicular distance between center of gravity and the pivot point is 2rh, 2 capital RH minus h square square root. All right, so then the net torque with respect to the pivot point is minus F capital R minus h parentheses plus mg r perpendicular, which is square root of h parentheses 2r minus h. And this must be equal to 0 at equilibrium. So that will give me the minimum force I need to just start the process. F is equal to mg, and then I have h r minus h in square root divided by, so this f was taken to the right hand side, this minus sign becomes plus, so this is divided by r minus h. Okay, so that gives me the final answer for the minimum force I need in this case when the force is applied at the center. In part B, the force is applied at the top of the wheel. Now the perpendicular distance between the point of application of the force and the pivot point is 2 capital R minus h. the perpendicular distance between center of gravity and the pivot point doesn't change. So if I look at this scenario, the net torque with respect to the pivot point is now minus F 2 capital R minus H. Once again, this torque is R cross F. It's in clockwise direction, negative torque. And then here I have plus mg R perpendicular, and that gives me minus F 2R minus H plus mg square root of H times 2 capital R minus H. And this must be equal to 0. And that gives me a minimum force of mg. And now this time I have H 2 capital R minus H square root divided by 2 capital R minus H. So this is the new minimum force. So I see that 2 capital R minus H will be greater than capital R minus H. Here I have here I have the square root, so this is going to be scaling as 1 over square root of R minus H. This will be scaling as 1 over square root, this is 1 over square root 2R minus H, this is 1 over square root R minus H. So less force, I see that less force is required when it is applied at the top of the wheel. Okay, once again, why is that? Because this is equal to mg square root H multiplied by 1 over square root of R minus H. And here this is mg square root H multiplied by 1 over square root 2R minus H. So square root 2R minus H is greater than square root R minus H. So this will correspond to a smaller number, so less force will be required. Okay, so we're looking at raising a wheel over a curb. What is the minimum force I need to apply at the center or at the top of the wheel in order to just make it turn? Now, in the first case, I have a perpendicular distance between the pivot point and point of application of the force, capital R minus H, because H is the height of the curb, and the perpendicular distance between the pivot point and center of gravity R perpendicular can be found using this right triangle, square root of R square minus parentheses R minus H square square root. This gives us H parentheses 2R minus H square root for R perpendicular. The torque due to this force is clockwise. The torque due to this force, R cross F, is counterclockwise. So they balance each other, and this gives me a minimum force, mg square root H 1 over square root R minus H. For the second scenario, the perpendicular distance changes from R minus H to 2R minus H. There's an additional R here. So once again, this is a negative torque. It is clockwise rotation, minus F to R minus H, and this torque due to the weight doesn't change, mg R perpendicular, and that gives me a minimum force, mg square root H 1 over square root 2R minus H. Since square root of 2R minus H is greater than square root of R minus H, I see that less force is required in this case. So when it is applied at the top of the wheel, we need less force to make it over the curb.